Good evening. This is the 26th lecture or the lecture series, Extra Crystallography and Solid State Chemistry. We are discussing about the structures of solids, groups of solid. I have not said solids, groups of solid. Okay, in the 25th lecture, we described details about how we describe the structure of solid and what are the methods we use to describe the structure of solids. And we are on these slides, we talked about this slide very quickly and did not explain detail. I think that we need to explain a bit detail of cesium chloride structure type. Okay, this is a primitive cubic structure. Why do you call it primitive cubic structure? Because, you see, here the body, the cesium chloride, cesium. In the body center, the cesium. But the corner of the cube is chloride. So if the cesium would be a chloride ion, chloride atom or so, then we would call it body center cubic. But since it is not, therefore it is a primitive cubic. And what else we have to discuss about it? Well, the coordination number of both cesium and chlorine are 8. And what is the interatomic distance? Interatomic distance is about 0.866 A. Interatomic distance between cesium and chloride is about 0.86 A. We have to remember we have been discussing about structure in close-packed arrangement. Cesium chloride is not a structure of which should be identified as close-packed arrangement. In a close-packed arrangement, what we have, the anion has gotten 12 coordination with other anions, neighbor anions. Here it is only 6, and therefore it is not a close-packed arrangement structure or close-packed structure. So it is octahedrally arranged structure. We have many different types of compounds we can identify as cesium chloride type structure. And they fall in 2 groups. One, the halides of large monovalent elements. Large monovalent elements, monovalent means that the oxygen state of the cation is +1. So we know alkali metal has got +1 oxygen state. And large, I said large monovalent. If we go for the group 1, we will see that cesium is the largest one we are thinking about. So all cesium halide, you see, all cesium halide or cesium cyanide, ammonium chloride do belong to cesium chloride structure. And here are the cell parameter. Here is cell parameter of those structures. Not only these, we have another group, varieties of molecule or compounds, which we call intermetallic compound, do belong to this type of structure. And you see, this is an intrametallic compound, copper zinc. And you see, all these are intrametallic, and these are cesium chloride type of structure, having the cell parameter here, which is in the table. How we can see the atomic position? We can see that if it is primitive chloride and unit cell of cesium chloride, chloride has got a coordination, has got a position 0, 0, 0, and cesium at half, half, half. Okay, now that we are talking about another important compound, lanthanum boride. Lanthanum boride is hexaboride. How we describe this structure in cesium chloride? You do remember that we have to have this boride cluster ion in place of chlorine, and cesium lanthanum will be sitting in place of cesium. So there we see, we describe the structure of cesium chloride, and we see the different aspects of cesium chloride structure. We said in the beginning that cesium chloride is not a cubic closed spec structure, but there is a link between cubic closed spec structure. Also, that closed spec structure, not cubic closed spec structure. Fluoride structure is closed spec structure, which is described as primitive cubic array of anions with cations in alternative cubic body centers. In cesium chloride, we see that all body center positions are occupied. We go to next slide, and this is a very important class of compound, very, very important class of compound. It's perovskite, and the general formula of perovskite is AbX3. We can typify one example. Ab is the cation, A and the cation, B another cation, and X anion. If we typify this perovskite with the strontium titanium oxide, which is a projection of strontium titanium oxide is here, projection. Well, this strontium titanium is a primitive cubic unit cell. You see, in A and B we are seeing projection, and this is titanium, strontium, titanium. This is strontium. This is oxygen, and we also show the position of strontium as well as titanium here. There are two ways we can describe this perovskite. One, the titanium is in the cube corner. You see, this is titanium, which is in the cube corner. Do remember that we are looking to this structure in one axial length. And then titanium is in cubic, so its coordinate is, titanium's coordinate is 0, 0, 0. And strontium, as it's in the body center, so it should be half, half, half. And oxygen at the edge of the edge center, and therefore the oxygen coordination will be half, 0, 0, or 0, half, 0, or 0, 0, half. The other way of describing it, which contains strontium at the corners, there it is, strontium at the corner, and titanium at the body center. Titanium is at the body center. Other way of describing, I see. So, and the oxygen at the face centers. These two descriptions are interchangeable. We can interchange this and simply related by translation of the origin halfway along the cube body diagonal. That's what we see in this diagram. In this diagram as well as in this diagram, we can see this. Okay, the octahedral coordination environment of titanium is seen in this figure, and then the interatomic distance, we can calculate the interatomic distance from this diagram, and we find it. Titanium oxygen distance is A/2. It comes to be around 1.953 angstrom. Strontium is equidistant from oxygen, 12 oxygen, and strontium oxygen distance is equals half of the diagonal of any phase, and that is about 2.76 angstrom. Another thing that if we perovskite, we said it is not a closed spec structure as such, but oxygen and strontium, if we consider together and do form a cubic closed spec arrangement here together, and this figure we can see closed spec arrangement, which is parallel to plane 1, 1, 1, shown C and also in E. Another thing of this perovskite structure that we can see here, that F, this perovskite is also regarded as framework structure with corner sharing titanium oxygen octahedra, and with strontium in 12 coordination interstices. Okay, so here we see this, and if we perpendicular to this plane of paper, if we link this titanium oxygen titanium linearly, then the shape forms a three-dimensional framework of this, one. This is what we call describe. This is how we describe the perovskite structure. Now we go to the next slide. With hundreds and compounds, hundreds and hundreds of compounds of oxide and halides can be seen as perovskite structure. Two cation oxidant state should be altogether 6. For example, if we take this one as a perovskite structure, this one has got oxygen state +1 and niobium is +5. So into total, this is 6 oxygen state, both of the cations. If we take calcium titanium oxide, which is also perovskite, and we see the 2 + 4, 6. And then if we take this lanthanum gadolinium oxides, and we see that this has got 3 + 3. So in total, we can see that oxygen state is 6. The 12 coordinate A sites cation are of course much larger than the 6 coordinate B sites. So this A site is 12 coordinated and this site is 6 coordinated. That is what that is how we describe it. And we can see that there are very few compound we take here in the table which show perovskite structure, that potassium niobate, potassium pentachlate, and potassium iodate, and other like this. What is that? And here it is the cell parameters of this compound. You can see that many compounds. We say the oxides and halides of 2 cations, mixed cations. Okay, the cubic structure, perovskite structure described so far. So far, we have been describing about cubic, but a variety of distortion, which gives us non-cubic structure existing, having lower symmetry structure. We will see that this is one. We are talking about another type, which is the lower symmetry than that of cubic, and barium titanate, which is as a tetragonal at room temperature, and cell parameter A is 3.99 and C is 4.034. And this is a tilted perovskite structure of gadolinium iron oxides, twisted and tilted structure. And lower symmetry structure exists when we, and the framework of octahedra, then slightly distorted. Okay, now here, if we take this barium titanate, you see that we have, this is a projection of barium titanate, and one thing we see that this titanium oxide, titanium is slightly too small for octahedral size, and this is displaced by about 6% of the titanium oxygen distant towards one of the corner of barium. This lies slightly distant. And for this displacement, the coordination of titanium is square pyramidal than that of octahedral. You see, and the projection, or what I say, projection is to show this in this structure. Well, another distortion of type of distortion of perovskite, which we have to discuss, that perovskite whose tolerance factor is less than unity. Then we see structural distortion mode. And And a three-dimensional Feynman structure, for instance, we are showing here that how the distortion occurs, and this distortion theoretically possible, which has been which has been shown by Glaser and Alexandrov. This widely used as Glaser method, and the following methods are taken into consideration for explaining the distortion. What are these? The undistorted perovskite, if the three axes of the octahedron are given, so let's say with three axes we give the octahedron as A, B, C, and if the degree of any rotation about all these three axes are same, if rotation all the three axes are same, then we labeled this as AAA distortion. If rotation about one of the axes is different, let's say we said three of the axes should be same, then we call it AAA. But if one of these three axes are different, then we say that, for example, it's different in C, we call it AAC. So another assumption that each of these letters carries a subscript. If there is no rotation about that axis, then we call it zero. For example, you see A0, A0. If there is no rotation about this axis, we call it. For example, if there is rotation, then we see what type of rotation it is. If the rotation between adjacent octahedra is the same and in phase, the subscript should be plus. And if the rotation between adjacent planes in opposite sense, the subscript is minus. Then here it is. Yeah. This is minus, and therefore, if it is in phase, that is plus. These are the three way of describing perhaps a distorted perovskite structure. Okay, the details of this analysis are not in the syllabus which you are following to prepare the lecture series. So therefore, we stop this discussion here. Anybody interested, one can go in the book. We said we give the reference in the very beginning. So you can go and read more about it. Okay. So then, as we said that there are many other types, we say another recent interesting family of perovskite-related phases, which is calcium, copper, titanium, oxygen. In short, we say CCTO, because it has got giant dielectric constant and permittivities. So the bulk, this is the grain contracts of ceramics. We can see the structure here of this CCTO. And here is the structure. And this is what is titanium oxygen octahedra. We show it. The next structure we show is a copper oxygen square planar arrangement. Well, I have been also discussing about the space group and this. If we discuss the three-dimensional structure, we know that we mean one of the space group also. Here is the space group. This type of structure, this CCTO type of structure. The space group is IN bar 3, number 204. We know that we have one of the space groups, number 204. And this is the position, Wyckoff position, we call it. We show the position calcium in three-dimensionally, and it belongs to 2A Wyckoff position, copper 6B Wyckoff position, titanium 8C Wyckoff position, and oxygen 24G Wyckoff position. And the coordinates for this Wyckoff position is, but for copper it's 0, 0, 0, that means it is bound, and then 0, 0.25, 0.5 for copper. Calcium is 0, 0, 0, copper, this is the coordinate for copper. This is titanium coordinate 0.25, 0.25, 0.25, and this is oxygen coordinate. These are the oxygen coordinate, and in bracket it's the standard deviation of the position. So this is what is we have been discussing, and then we see the crystal structure, this right figure structure, in which the left part of the diagram emphasizes tilting of titanium oxygen octahedra, and right part of the diagram, that part is a square panel of copper-based units. And if we take the Glaser notation for this, we will see that it is A plus, A plus, A plus. This is what we have been discussing. And a wide range of composition of A prime 3, B4, oxygen. This is the cations and anions from the same structure of CCTO. A is an intermediate sized alkaline earth or rare earth cations such as sodium, calcium, lanthanum, potassium, natrium, or a lone pair P block cations, lead, bismuth, that occupies the 8 coordinate A prime size, 8 coordinate A size. And A prime size is either this cation copper 2 manganese 3 that occupies the square planar, and the square planar B sides is a transition metals, titanium, vanadium, manganese, iron, etc. And the structure are cubic with a cell parameter A and 2 AP. But AP means that the latest parameter of the perovskite subcells. So here we show the lattice parameter as well as the space group of these special type of compound CCTO. With this slide, I will stop here and continue with this perovskite type of structure in the next lecture, and hopefully we'll understand more about it by explaining a bit more in the next lecture. Thank you very much for this evening. Hope to see you in the next lecture again. Thank you. Thank you so much.